So what is this? We saw this shape back in part 1, and then proceeded to not talk about it for like 10 episodes. And at this point, I really wouldn't blame you if you thought this was some science fiction designed to get you excited about doing boring algebra problems. But before we chalk this up to unnecessary special effects, let's remember where this shape came from. We began our conversation in part 1 with an equation that appeared to have no solution, x squared plus 1 equals 0. And after all the work we've done so far, you can probably see how to find the answer algebraically. Subtract 1 from both sides of the equation and take the square root, resulting in x equals plus or minus I. Done. So that's cool, but to really make sense of our shape from part 1, we need to dig a little deeper and talk about functions of complex variables. The kinds of functions most of us are used to, functions of real numbers, have inputs and outputs that can be visualized using a single dimension. This means all our x values fit on a single number line, and so do our y values. It seems pretty reasonable then, that if we want to figure out how x and y are related, we should put our x number line facing one way on a piece of paper, and put our y number line on the same piece of paper, just facing the other way. This forms a two-dimensional grid known as the Cartesian coordinate system. Apparently invented by René Descartes in the 16th century after watching flies crawl around, the Cartesian coordinate system is a super powerful tool for understanding the relationship between two variables. The Cartesian coordinate system is powerful because it allows us to take abstract ideas like functions and turn them into something our brains can grasp much more intuitively: shapes. By giving each point on the plane its very own coordinates, Descartes was able to bring together the two largest areas of mathematics at the time: algebra and geometry. This greatly aided early efforts at classifying functions by Newton and others, and today the Cartesian coordinate system shows up everywhere, helping us do all kinds of things like spot trends in data. So that's all fun and wonderful, but the Cartesian coordinate system does come with a disclaimer. It only works in two dimensions. This limitation becomes a real problem when we start to think about functions of complex variables. These functions take in complex numbers for their inputs, and for the most part also output complex numbers. This means the numbers we put in and get out of our function no longer fit on number lines. We need two complex planes to keep track of our numbers, one for our input and one for our output. This raises an important question. If, when visualizing these functions, what we're really interested in is the connection between the input and output, how do we visualize what's happening on both planes simultaneously? We could try to fit our input and output planes together somehow, as we did with our number lines for real valued functions, but we quickly run into a pretty serious issue. As you likely know, the universe we live in has 3 spatial dimensions. So there's no way to fit the 4 spatial dimensions we need into a single structure that our brains can comprehend. We simply run out of dimensions. Fortunately, there are some very clever ways to see the relationship between two complex variables. But before we can get to these, we need to think about the mathematics of complex functions. Even though using separate planes for our input and output is not a perfect solution, this approach can still help get us started. Let's try it out with our original function, f of x equals x squared plus 1. Before we begin, let's make a quick variable change to make things easier down the road. We'll change the name of our input variable from x to z and call our output variable w. Since z and w each have a real and imaginary part, let's go one step further and give these parts names. We'll let z equal x plus iy, so x represents the real part of z, and y represents the imaginary part. We'll also let w equal u plus iv. Just as we can use tables to keep track of our inputs and outputs for real valued functions, we can also use tables to keep track of our inputs and outputs for complex functions. However, we now need 4 columns to keep track of our 4 variables, x, y, u, and v. We can now experiment with our function f of z equals z squared plus 1. If we plug in a complex number to our function, for example z equals 1 plus I, we can do a little algebra and obtain our result, w equals 1 plus 2i. Plotting our inputs and outputs, we see that the point 1 plus I in our input plane was pushed or mapped by our function to 1 plus 2i in our output plane. Let's plug in a few more points here and see if we can find a pattern. If we test points along a straight line in our input space, we see that in our output space, our straight line is transformed into a curved line. Interesting. As you can imagine, plugging in points like this can get pretty tedious. To speed things up, let's let a computer do it for us. And instead of having our computer just map certain points, let's have it map all the points. We'll take advantage of the fact that the image you're seeing is just a collection of pixels that happen to be arranged on a grid. We'll use some code written in the programming language Python to move every single pixel in our input space to its proper location in the output space. To make this work, we'll assign each pixel in our input video a complex number that corresponds to its location on the complex plane. We can then let our code take care of the tedious work of moving each pixel to its new location, as dictated by our function, z² + 1. Our code will move points exactly as we did by hand before. If we have a blue pixel at the 1 + I location on our input graph, then this blue pixel will be moved to the 1 + 2i location on our output graph, because f of 1 + I is equal to 1 + 2i. We saw before that our function warped a straight horizontal line into a curvy one, so it should have some interesting effects on our video. We'll include some reference markers on top of our input and output planes to keep track of our numbers, but we won't transform these pixels. Alright, ready? Let's start by drawing some simple lines. A horizontal line along the positive x-axis turns out to be something pretty similar in our output space. But what about a line along the positive imaginary axis? This line appears to have been rotated. As we add more lines, we begin to see a pattern. Our family of straight lines is turned into a family of curved lines. Cool, right? So we found one pattern, but how is this pattern explained by our function z² + 1? And more importantly, how does this fit with everything else we've learned about complex numbers? What else would be interesting to draw in our input space to test our mapping? What shape would you draw to learn more about what our function is doing? Next time, more shapes.